Insertion sort is a sorting algorithm where, given a list of values as input, it will sort them in ascending order. Here is our agenda for today. First, we will do a quick example of insertion sort just to jog your memory. Then we will discuss the general procedure of the algorithm in plain English. Next, we will introduce the idea of big O and use this to analyze the complexity of insertion sort. Here's the main idea behind insertion sort. At each step, there is a sorted portion of your list and an unsorted portion. We build the sorted portion by repeatedly grabbing the leftmost value in the unsorted portion, scanning backwards right to left until we find the value's appropriate position in the sorted sublist, and then inserting the value at that position. Here is the slightly more detailed insertion sort procedure, where all we're really going to add is a loop counter I, which keeps track of where the unsorted portion of the list begins, and a place marker sort pose, which keeps track of our place while scanning backwards through the sorted portion. Let's see it done real fast. In analyzing the performance of an algorithm, we care about how it behaves depending on the size of the input. Big O is a way to measure performance as the input size increases. So how do we gauge performance? It can be in terms of steps taken or runtime, or the amount of memory required to perform the computation. So you can see in the visual, we have input size on the x-axis and steps taken on the y-axis. Each of these curves you can think of as plotting the number of steps a given algorithm took when the input size was x. Here is how you do a big O complexity analysis. First, you need to derive a formula determining how many steps an algorithm takes for a generic list of size n, we'll call it. Then you remove constant coefficients and any terms that are dominated as the input size grows towards infinity. This means that as the input size gets larger and larger, we identify which terms become insignificant to the overall behavior of the algorithm. So we'll do an example. Let's say that we determined a formula for the number of steps an algorithm took, and it was n squared plus 10n plus 100 steps. What would the big O runtime complexity be for this algorithm? First, we remove constant coefficients. That's 10 and 100 here. Then we remove terms that are dominated as the input size increases. But how do we do this? Well, there are numerical ways we can do it, but to illustrate the idea, let's look at some graphs. We plot each of the terms, n squared in green, 10n in red, and 100 in gray. We can see that for a small input size, less than 5, the 100 term does matter. But when the input size is 10, all terms are equally significant. When the input size is 20, n squared and 10n clearly surpass 100. When the input size is 100, we can't even see the linear and the quadratic terms anymore. And when the input size is 1000, n squared is clearly increasing more rapidly than the other terms, and this gap will become even more pronounced as the input gets larger. So we can say that n squared is the term that dominates here. So we remove the terms that are dominated as the input grows towards infinity, and all we have left is n squared. So we can say that the algorithm runs at O of n squared. So the best case for insertion sort is when the list is already sorted. None of the values need to move because they're already in their correct positions. What happens is, on each iteration, we do one comparison and find out the value left of the current value is not greater, so neither value needs to be repositioned. Let's see an example. So we start with the values 6, 7, 8, 8, 9. And I just want you to note which comes first in the original list. 8 of hearts or 8 of spades. So initially I is at position 1, sort pose is there too, and 7's the curve value. The values left of 7 form a sorted sublist. Should 7 go right of 6? Yes, so 7 stays. The first two values are sorted. Now the curve value is the 8 of hearts. Should 8 go right of 7? Yes, it's greater. Now the first three values are sorted. I and sort pose move to position 3. And the 8 of spades is the curve value. There's no point in moving the 8 of spades left. The first four values are sorted as it is. In fact, recall that the original order of the 8s was the 8 of hearts first and then the 8 of spades second, so it stayed that way. And by preserving this original order of the equal elements, insertion sort can be considered a stable sort. Anyways, the first four values are sorted. I and sort pose move to position 4, and 9 is the curve value. Should 9 go right of 8? Yes, 9 is greater, so it stays where it is. Now all 5 values are sorted, and we have made 4 comparisons. So now you've seen that we do n-1 iterations, making a comparison on each iteration. So if we tack off the constant, all we're left with is O of n.